The world is rapidly changing. Software is everywhere. From the apps on our phones to the systems that run our cities, software is the backbone of modern life. As our reliance on software grows, so does the need for efficient and effective software testing. Traditional methods are no longer sufficient to keep up with the pace of development and the complexity of modern applications. AI is now crucial in software testing. It has revolutionized the way we approach quality assurance. By leveraging machine learning and advanced algorithms, AI can predict potential issues before they become critical, ensuring a smoother user experience. It helps create better, faster, and more reliable software. Developers can now focus on innovation rather than getting bogged down by repetitive testing tasks. AI-driven tools can run thousands of tests in a fraction of the time it would take a human, providing instant feedback and allowing for rapid iteration. AI can analyze vast amounts of data, identify patterns, and automate repetitive tasks, freeing up human testers for more complex and creative work. This collaboration between human intelligence and artificial intelligence leads to more thorough and nuanced testing processes. However, the power of AI in software testing comes with its own set of challenges. Integrating AI into existing workflows can be complex and requires a deep understanding of both the technology and the domain it is being applied to. One of the most significant of these is the dilemma of AI accuracy. While AI can process data at incredible speeds, the quality of its output is only as good as the data it is trained on. Poor quality or biased data can lead to inaccurate results. AI algorithms, while powerful, are not infallible. They require constant monitoring and fine-tuning to ensure they are functioning correctly. This means that human oversight is still crucial in the software testing process. They can, and sometimes do, make mistakes, leading to false positives and false negatives in test results. These errors can have significant consequences, from minor bugs to major system failures. Therefore, a balanced approach that combines the strengths of AI with the critical thinking and problem-solving abilities of human testers is essential for achieving the best results in software testing. In the context of software testing, accuracy refers to the ability of an AI system to correctly identify and classify defects in software code or functionality. This means accurately distinguishing between actual bugs and harmless anomalies. When an AI system flags a section of code as faulty when it is in fact working correctly, this is known as a false positive. Conversely, when the system fails to identify an actual bug, this is called a false negative. Both types of errors can have significant consequences in software development. False positives are a common problem in AI-driven testing. These occur when the AI model, trained on a specific set of data, encounters an unfamiliar pattern or anomaly in the code and misinterprets it as a defect. This can lead to wasted time and resources as developers chase down non-existent bugs. Furthermore, a high rate of false positives can erode trust in the AI system itself. Developers may start to ignore or override its recommendations, potentially missing real defects in the process. This underscores the need for strategies to minimize false positives. False positives are a common problem in AI-driven testing. They occur when the AI model, trained on a specific set of data, encounters an unfamiliar pattern or anomaly in the code and misinterprets it as a defect. This can lead to wasted time and resources as developers chase down non-existent bugs. Furthermore, a high rate of false positives can erode trust in the AI system itself. Developers may start to ignore or override its recommendations, potentially missing real defects in the process. This underscores the need for strategies to minimize false positives. This can lead to wasted time and resources as developers chase down non-existent bugs. Furthermore, a high rate of false positives can erode trust in the AI system itself. Developers may start to ignore or override its recommendations, potentially missing real defects in the process. This underscores the need for strategies to minimize false positives. Furthermore, a high rate of false positives can erode trust in the AI system itself. Developers may start to ignore or override its recommendations, potentially missing real defects in the process. This underscores the need for strategies to minimize false positives. Developers may start to ignore or override its recommendations, potentially missing real defects in the process. This underscores the need for strategies to minimize false positives. This underscores the need for strategies to minimize false positives. While false positives are frustrating, false negatives pose a more serious threat. A false negative occurs when an AI system fails to identify a genuine defect in the software. This can have severe consequences, as undetected bugs can lead to software crashes, security vulnerabilities, and data breaches. The insidious nature of false negatives lies in their invisibility. Unlike false positives, which are immediately apparent, false negatives can lurk undetected in the codebase until the software is released, potentially causing significant damage. Section 5. The high stakes, why accuracy matters. The accuracy of AI-driven testing is not just a technical issue, it has significant business implications. In today's fast-paced software development landscape, speed and efficiency are paramount. However, these should not come at the expense of quality and reliability. Inaccurate test results can lead to delays in software releases, costly rework, and damage to brand reputation. In extreme cases, they can even have legal and financial ramifications, particularly in industries where software failure can have life-threatening consequences. Section 6. Real-world repercussions of AI inaccuracy. The impact of AI inaccuracy in software testing is not merely hypothetical. There are real-world examples where such inaccuracies have had significant consequences. One such example is the case of a self-driving car that was involved in a fatal accident due to a software error that failed to detect a pedestrian. In another instance, a major financial institution experienced a system outage that resulted in millions of dollars in losses. The outage was attributed to a software bug that had gone undetected during testing. Section 7. Balancing sensitivity and specificity. A key challenge in AI accuracy is finding the right balance between sensitivity and specificity. This balance is crucial because it directly impacts the performance and reliability of AI systems. Sensitivity and specificity are two sides of the same coin, and achieving the right equilibrium can be quite complex. Sensitivity refers to the AI's ability to correctly identify positive cases, that is, actual defects. High sensitivity ensures that most of the true positives are detected, which is particularly important in scenarios where missing a positive case could have serious consequences, such as in medical diagnoses or critical system monitoring. Specificity, on the other hand, refers to its ability to correctly identify negative cases, meaning code that is free of defects. High specificity is essential in reducing the number of false positives, which can lead to unnecessary actions, wasted resources, and potential frustration among users. Increasing sensitivity may lead to more false positives, which means the AI might flag too many non-defective cases as defective. This can overwhelm the system with false alarms, making it difficult to identify real issues and potentially causing users to lose trust in the AI's recommendations. While increasing specificity may result in more false negatives, where the AI fails to detect actual defects. This can be equally problematic, as it means real issues might go unnoticed, leading to potential failures or undetected problems that could escalate over time. Finding the optimal balance depends on the specific context and the potential consequences of each type of error. In some cases, it might be more critical to avoid false negatives, while in others, minimizing false positives could be the priority. This delicate balancing act requires continuous monitoring, adjustment, and a deep understanding of the domain in which the AI operates. By carefully tuning sensitivity and specificity, we can enhance the effectiveness and trustworthiness of AI systems, ensuring they deliver accurate and reliable results. Section 8. Strategies for enhanced AI accuracy. There are several strategies and best practices that can be employed to enhance the accuracy of AI-driven software testing. One approach is to ensure the AI model is trained on a large and diverse dataset that accurately reflects the real-world scenarios the software is likely to encounter. Another important aspect is continuous monitoring and improvement of the AI model. As the software evolves and new data becomes available, the model needs to be retrained and refined to maintain its accuracy. Section 9. The road ahead, continuous improvement. The quest for AI accuracy in software testing is an ongoing journey, not a destination. As AI systems become more sophisticated and integrated into the software development lifecycle, it is crucial to remain vigilant about the potential for errors and to continuously strive for improvement. By embracing a culture of continuous learning, adopting best practices, and leveraging the latest advancements in AI, we can harness the power of this technology to build more reliable, robust, and trustworthy software for the future.